Hello, welcome to Chapter 4, Programming Paradigm, First Programming Paradigm, Imperative Programming, Lecture 4, Imperative Programming. Objective, Program Design Paradigm. So in this lecture, we are going to introduce the first programming paradigm. So a programming paradigm is the way you do programming, the way you think, the way you express your own idea. So today we are going to talk about the first one, that is imperative programming. And imperative means giving order, imperial. Okay, so it actually is instructional. So you give some orders, you have some instructions, you order your program to do something. So basically it's command by command by command by command. Okay, so that's called imperative programming. And in terms of hardware, it is the maneuver machine with a state machine with the memory. Okay, so that's the model of the imperative programming. So today we are going to talk about structural programming and maybe also talk about the push-down automata with the state. Okay, and then call and return sequence. These are the topics that we have in this chapter. So it is traditional programming, so it is not considered to be a hard chapter. So programming paradigms, we do have imperative programming, that is using the so-called instruction after instruction. That's one kind of instruction, that's one kind of programming paradigm. And in here we have structural programming paradigm, also called as structural programming paradigm, that a procedural programming paradigm that has the if then else structure and also functions. Okay, and then we may also have object-oriented programming paradigm that using object, method, and member function. And object-oriented programming is considered to include a procedural programming paradigm. And then we have parallel programming that has a fork, join, and parallel processing, but each of the threads can still be a procedural programming paradigm. So left-hand side, it's all imperative programming. It is considered to be function after function or instruction after instruction. Right-hand side, you have declaration, a declarative programming paradigm. This kind of declarative programming paradigm, usually you have definition of the rule. Okay, and you also may have the definition of the fact. And based on the facts and rule, you do reasoning. So 3 portions. Usually you have 3 portions. So fact, rule, and reasoning. And you have logical programming. So logical programming has facts and rule, and you have derivation. Okay. And then you have function, calling function, that's a functional programming. You have data flow approach, that's also declarative programming. So usually SQL is considered also to be as declarative programming languages. So here you have different paradigm and you have different programming languages. And interpreter, we have C, Fortran, Basic, that's imperative. We do have SQL, Clip, Prolog, that actually is logic type. Okay, these are 2 extremes. And then we have functional, called ML, Haskell, Scheme, Common Lisp. We have object-oriented programming that has the Object-C, Java, FL, Smalltalk. We have multi-paradigms, C#, Ruby, Perl, Python, and Dylan. Okay, on these different function or different programming paradigm approach, including the syntax, semantics, binding, scope, parameter passing, control, and type. And then there would be some interpreter to do that kind of design. So here we introduce different programming paradigm and also the different language that belong to them. And we have procedural programming. Outside, you have structural programming and you have imperative programming. That's the first chapter that we want to talk about. And procedural programming, you have procedure, and you may go into some block 1D array, and you may have procedure go over 3. You may have procedure go over 2-dimensional array. You may have procedure go into some block or some hierarchical design. Okay, object-oriented programming. Object-oriented programming treated the program as a class, and class may have create instance. And object-oriented programming is based on the imperial programming, the procedural programming. Beyond that, you also use an object-oriented thinking way to actually encapsulate your object and the methods into a capsule, the object. And then class to class relationship, you have the inheritance and polymorphism. Polymorphism may make the code reusable and using the dynamic linking. So basic 3 major factors of the object-oriented programming is encapsulation, inheritance, and polymorphism. And sometimes the object, we can also say it has the abstraction because you hide the technical detail from people. So these are the basic idea of object-oriented programming. And an object, including the private data, okay, and public methods, and you can only allow the outside function or program to access the object using the public methods. And object-oriented programming can be used into event-driven programming, and each event may have event object, event source, event target, event handler. So you create an event on your event source, you click a mouse, okay, create an event, and then you trigger a login button that's trigger an event, and those events will create event object and put into the event queue, and then your event loop will process on it, and your event loop will call the callback function or the event handler to handle it. Okay, so these are the event-driven programming, and event-driven programming has been proven to be very good to be implemented by object-oriented programming. So in Windows programming environment, event-driven programming, object-oriented programming, and Windows programming can be considered to be similar things. And we have been using that for quite a while. And then this is one kind of application for object-oriented programming. So you have the event, putting them into event queue, and event queue would wait for the event to be processed and handled by event handler. And you have multi-threading. Multi-threading, you have Java, Spark, Hadoop, Quasar. So multi-threading allow you to go parallel. And here we have the declarative programming, we have functional programming, and functional programming have referential transparency, functional composition, pure function, refactoring, higher order function, coroutine, and immutability. So these are the topics in functional programming. Okay, so here in chapter 1, in chapter 4, we focus on imperative programming. So imperative programming paradigm, here we compare the declarative and imperative. So imperative programming has command, manipulate state of the program of the system and variable, and many side effects. And declarative usually have no side effect. And imperative, you usually can change the variables data, and declarative usually don't change the data's content, even though you have set Q or set exclamation mark to set a variable, but usually you just get the output and feedback to another function, and another function call another function and return something, and usually you don't change the data, you just forwarding the data. And so declarative usually utilize the data flow, and then imperative programming using the control flow. So imperative programming usually is talking about a nonlinear machine has a control unit and memory. Sequential programming. Okay, the first type of the imperative programming is sequential programming. Sequential programming is step by step by step. Okay, and then the only way you can jump or you go from your main routine would be branch or jump, and using go to or jump on 0 or jump on equals. Okay, so this simple function of the sequencing one by one and go to form the basic programming for the so-called sequential programming, step-by-step programming. And here, this is the first unit. This is very simple control unit. And usually, COBOL language or the Fortran or assembly using this kind of the unstructured control flow sequencing and go-to function. And unstructured control flow use the go-to statement a lot. And nowadays, this kind of the go-to is not commonly used, and we don't encourage people to use that. Okay, but we just talk about this, the old days programming is sequential, is specify linear ordering on statement and one statement after another, and very pure imperative manual machine. A compound statement is a delimited list of statements. So compound statement is a code block. And then when it includes variable declaration and CC++ Java using brackets, curly braces to delimit a block. Pascal using begin end. Ada use declare begin end. So this is a code block. Okay, code block. Okay, assembly. On the right-hand side, you have C language. So integer n equals 3, quit it. Okay, go to quit it. So you go to quit it, and then you return x. Okay. This one actually you will never run the x equal 999. Okay. So this move register with 3. And then jump unconditionally. Unconditionally jump, you just jump. There is no if then else involved. So the move 999 to EAX will not be run. Okay. So this jump, assembly unconditional jump, and also go to function on the right side. So we also may have range function and jump. Okay. And jump, you have unconditional jump, jump greater than, jump above equal, jump below, and jump below equal, jump on sign overflow, jump, okay, equals whatever condition, ECX register with 0, and jump equals, so when there's a register is equal, jump greater than, jump greater equal, jump less than, jump less equal, and jump not equal, jump overflow. And you have jump with unsigned variable and jump with signed variable. So these are two sets of the jump instruction, and you operate on the two's complement or not two's complement, that you need different functions, different instruction. So left-hand side, we have jump if equal. So move EAX with 3, compare EAX with 3. So if this statement will set the equality flag, so you set the flag, and then the jump equal will based on this compare result. If it's equal, okay, if EAX equal, and then usually here it will be equal, it will jump to here, and this portion will not be wrong because it's always equal. Okay, so here if we have the jump less than, this one is 1, so 1 compared with 3 is less than, so jump less than, we will actually jump to here. This one will also not wrong. Okay, jump less than. Okay, expression evaluation. So we talk about sequential programming. Now we're talking about the selection, iteration, procedural abstraction, and the recursion. Okay. And expression evaluation, we have infix expression, postfix expression, and prefix expression. Okay, and later chapter we will see it. Okay, and we have different expression, and expression had infix operator, prefix operator, and the postfix operators. And usually in normal language is using the infix operators, but the compiler may need to convert it to postfix operators. Okay, so C language has 15 different levels, and there's a lot. Okay, and Python may only have 6 or 8 levels, so it's actually way easier. And here actually we just need to know this one. This one will be C language and ADAS language, and also Python language as operator precedence level. Okay, and expression evaluation. So ordering of operand evaluation, generally none. Application of arithmetic identity. So here we have A plus B plus C work if A less than maximum integer and B less than maximum integer and C less than 0. Okay, it will work. Okay, so here let's see, actually equal maximum integer, not equal maximum integer, and B not equals minimum integer. Okay, here is a condition you will work. Okay, you need to avoid the overflow condition. Okay. Okay, so here consider A less than B and B less than C. If A greater equal C, there's no point evaluating whether B less than C, because A less than C and C less than C is automatically false. So this one we call it short circuiting. Actually, this portion, if this one is wrong, and the operator will not evaluate this because you have a false and whatever, it actually doesn't care. So this portion will not be evaluated. We call it short circuiting. Okay, if you using or and. On the other hand, you have expression or expression 2. Okay, then if this was true, the second portion will not be evaluated as well. Okay, so here if B not equal 0, okay, and if this one B equal 0, then the second portion will not be evaluated. So you will not see the A divided by 0 exception. So this one is so-called short circuiting. Evaluation number 2, orthogonality. So orthogonality actually is meaning that feature that can be used in any combination. So you can put a function to where function accepted. You can put an integer at where integer accepted. You can put a Boolean value at where Boolean value being accepted. We call it orthogonality. Okay, and A divided by B equals C if B equals 0, else false. Okay, so if B equals 0, so you evaluate B equals 0 first. Okay, if E equals 0, not equal 0, then we will return this value. Otherwise, we will return false. Okay. Okay. So assignment statement is executed for its side effect. Okay. Some statement has side effect. So assignment operator plus equal, that's actually is increased by or decreased by. This augmented, this two operator, we call it augmented operator assignment. It is handy and avoid a redundant word. Okay, and perform the side effect. Side effect is assignment. Okay, so it's increment and then assign. So it actually has a side effect. And we have C increase and C decrease. That's a postfix format. Okay, side effect often discussed in context of function. Side effect is the functions that is not something you desire or you design to be. So basically, you have a function, and function is a black box. If your input and output relationship only depend on your input, then we call it pure function. So there's no side effect. But side effect means you have the input and you have the output, but you will also affect somebody or being affected by somebody. That actually is called side effect. That's not pure functionality. That we call it side effect. Okay. So side effects are fundamental to the whole von Neumann model of computing. So sometimes we like the side effect in von Neumann computing. Okay, because you have the assignment, but the assignment also returns some value. That's called side effect. In pure logical or functional programming, no side effect. And these languages called single assignment languages. And several languages outlaw the side effect for functions, easier to prove things about programs. and closer to mathematical intuition. So we like to have pure function and then do not allow the side effect, especially for functions, okay? And here, if we have a global X, and then you set the X, and then it's not input-output relationship, you actually affecting some global variable, this we can consider that as a side effect, okay? And random number generator is also side effect. We do not have input, but we generate something unwanted, okay, undesigned, because it's a random number generator. So this is a good side effect. So side effects sometimes good. Side effects are particularly a particular property that it affects the state used in the other part of the expression. Okay, so if you affect some result, okay, for example, like A equals B, and then if we do if A equals B, you assign some value, say the B's value. So if B is 1, it becomes true. So that may affecting your program execution. So that's some sort of side effect that we don't like. Okay, so Fortune says it's okay to have side effect. Okay, anyway, side effect happen on imperative programming, and some languages do like it. Control structure selection. So here we go through the selection. A selection is if then else, switch statement, conditional statement, and these are called a basic operator or program structure for selection. So structural programming paradigm aim to improve the clarity, so we avoid the go-to and use the subroutine, control block, for loop, while loop, and if then else. This is called structural programming. So basically, make everything to be compatible with flowchart. That's called structured programming. And go-to function usually violate the structure. So we don't like the jump or go-to statement. And we call those kind of program as spaghetti code, causing difficulty to both follow and maintain. So here we have one by one sequential programming. We have left-right conditional programming. We have check and repetition, check and repeat, while loop or for loop type structure. So these are the basic statements: sequential and selection and also repetition. Okay, and structure control flow. Statement sequencing, selection with if then else statement, and the switch statement. This we call it the selection. Okay, iteration with for loop, while loop. It may also have the conditional testing. It is also structural control flow. Okay, and all of these promote the structured programming. Okay, and there's a break levels, pass, continue, break, return, and exit. This actually is somewhat not structural. Okay, somewhat not structural, but it's good to have that. Okay, Cobra with statement, compound statement, program structure and loop, and procedure and function. Okay, and selection we have condition, statement, switch, if then else. Okay, these are the basic statements in selection. In control section 1, we talk about the selection, and it has the if statement and also has the else statement. And those statements are very simple, so we do not spend too much time on it. So right now we move on to the next one, that's iteration. So basically, structural programming, we have the selection, okay, that if then else, selection, yes or no, okay, true or false. That's one thing. Second is we may have iteration like while loop, for loop, okay. Third one, we have the functional code, okay. So right here, what I'm drawing is the flowchart. Okay, you go to some program, and then you finish and come back. Okay, that's a function. So now we are going to move on to the iteration. Okay, we are going to move on to the iteration, and okay. So loop, while loop, for loop, and do while loop, and for loop and for each loop. These are different loops. Okay, some of the loop that actually Python doesn't have. Python only has a while loop and for each loop. There is no do while loop, no for loop. Okay, no regular for loop. It only has the for each loop. So let's look at these different loops. First one is the iteration. Okay, so iteration is you iterate through certain number or certain control variable or state variable. So you can iterate through every statement and go through it several times and repeat a collection of statement a number of times, where in each iteration loop index variable take the next value of the set of a set of values. So basically, you usually see there's a for loop for I equals 0, I less than something. Okay, those are the for loop. Okay, so here because Python is not complete. Okay, so we may use C++ or we may use Java to help to explain this different loop. So now let's continue. First one, let's look at the while loop. Okay, while loop is the same for different languages. Same thing right here. I'm going to move my slides to the left half. Okay, I'm going to open my Visual Studio Code over here. Okay, so first thing is we would like to look at the while loop. Okay. The while loop is simple. Basically, you have while, and here you have the continue condition. Okay, so it will be a Boolean variable over here. So usually, what we do actually is, let me use an example of getting the input. Okay, so let's assume that we have some variable called age. Okay, and this age would be a integer. Okay, and then we want to see if this age can be successfully input. So this age will be equals input or enter your age. Okay, enter your age. Okay, and then we may actually do what? We may do convert it to integer. Okay, you use an integer or you use eval function, either way should be fine. Okay, and that is my age, and I can print my age. Okay, print my age. Okay, so that's actually wrong. Okay, so right here we do get enter your age. Okay, sorry, this one in the code runner here I cannot input. Okay, code runner doesn't allow input. So this one I have to choose terminal. Okay, choose terminal, and I close my file browser. And right here, let me do Python. Okay, while okay, enter your age. So let's enter 15, and then you get out. Okay, so this is successful. Let's actually try another one. Python while the py, and here let me enter ABC. Okay, ABC, and it will break. Okay, so wrong data type, it will break. So here I'm going to write a input validation loop to prevent this from happening. So I'm trying to get this age, but it will throw exception if the data type is wrong. Okay, so now what I can do is, instead of doing this, I'm going to do while. Okay, not done. Okay, I'm going to get my age. Okay, I'm going to get my age. So here I should have my done equal false at the beginning. Okay, and here I want to have the same age variable, so I need to declare my age first, so it won't become a local variable in the loop. Okay, so age equals 0 over here. So we get this one, and it may have error, so I'm going to use a try. Okay, a try actually is exception. So when this data type is wrong, you show exception. So here I will actually take the actually except. Okay, and here I'm going to do print. Okay, wrong input format. Okay, wrong input format. Okay, and if your data type is correct, I'm going to say down equals true. Okay, down equals true. So this one is a simple input validation loop. Okay, I'm not going to use this as simple loop because everybody know it. Okay, so I'm going to use this one as example. That's an input validation loop. So basically, there is an exit condition. When will be it will be exit. When this not done, okay, not done's negation happen. This will be your exit condition, okay? Your exit the loop. So basically the post loop here, after your while loop here, you would have your post loop, post condition. The post condition will be not done, okay? And it actually really means that, okay, the input is done, okay, the input is done. So that's the exit condition. And not done is continue condition. The while loop will continue. So so when you design the while loop, remember the while condition, that is the continue condition. Okay, so let's run this one. Let's try this one more time. So Python, okay, while.py. So I'm going to try some error. Okay, it will give me the wrong input format. Okay, and then I enter 14, it will go through. Okay, so now your age sometimes maybe is invalid. So here you will say if age, okay, age must be greater or equal to 0. So if age is less than 0, okay, we are going to raise, okay, we are going to raise some exception, okay, some exception. So here let's raise a exception, okay, and this exception let's raise a string, okay, range error, okay. And this range error, it will be a basic exception, okay, it will be a basic exception, okay. So here except general case, okay, this one is general case, okay, it's except all kind of cases. So here we do except, okay, except what? Except base exception, okay. And then that's actually print my E, okay. E is an object, so you set a base exception object and you print E, okay. So that's actually try this one, okay, if the age less than 0. So let's do, okay, let's actually save this one. And here, let's do Python while.py, okay. And here, let me enter -4, okay. It will be range error, okay. So this one, I show you the exception, okay. This one actually in our chapter 4, right here, we do have a exception section. So let's finish this part as well. So exception is another type of control structure that you will accept when your data format is wrong or you have some error. Okay, you will go to here. Okay, so some exception is like this. You may have exception happening, and your program will break because you will have the exception, and you will see the error message, okay? So this happens pretty often that, okay, in the previous condition, we do see this kind of exception and your program break, okay? But we don't want that to stop your program, so we would need to provide an alternative route for it, okay? We would like to provide an alternative route for it. So we need to provide exception. So what happened is you will have a regular path, okay? And when the regular path have problem occur, you create exception, and the exception will be stored, and then there's an exception handler, okay? So here, okay, here actually when you have an input, okay, when there is an exception, the number will this whole thing will not be wrong. You will go to the exception and you check the exception. It's not basic exception, so you try the second one. If the format is wrong, you give you the wrong format. Okay, if the format is correct, okay, it got integer, but it division 10 modular by 2 is not 0, is not an even number. Then you will raise a base exception, and this exception will be captured by this statement, and you print that exception, okay? And remember that your string in here will be the message we carry to here. Okay, so you can use several exception, and each error type you can have different one. So let's see. Okay, here, okay, wrong range. Okay, here wrong range you can actually range. Okay, say is negative. Okay, and then here you can do another one if the age greater than 150. Okay, it's impossible that they are any person who can live more than 150. Okay, so this one you can copy here, and the error message you can put over here is actually say too large. So that actually save this one, and let's try again. So do Python. Okay, I'm sorry. Here, let's do 2.1. Okay, and then just do Python and while.py. Okay, and here let me give it 160 too large. Okay, -4. Okay, negative, and then blah blah blah. Okay, and then give them 54. Okay, these are the input validation loop combined with the while loop. Okay, I do not use the simple while loop because simple while loop is too simple and everybody know it. Okay, everybody know it. So this one, remember, this is exception handling. It's also another kind of the control structure. Okay, and we combine it with while loop. We combine it with while loop. So in this lecture here, I try to give you the explanation. So basically, the while loop is something like this. Okay, you have a try section. Okay, your regular section is here, and then you have an exception section. Your exception handler is here. Okay, exception handler is over here. Okay, so your regular case, if everything is true, you go through it, nothing wrong, you bypass and go to here. Okay, if there's something wrong, you stop and you jump to the exception, and anything after it will not be wrong. Okay, any after it will not be wrong. Once you finish the error handling, you come back to join the main thread. Okay, you come back to join the main thread. So this is the so-called exceptional handling, and it is another kind of the control structure. Okay, so right here we finish the while loop and this exception handling. Okay, that's the first loop called while loop. There's a do while loop. Okay, the do while loop, our Python doesn't have the do while loop. Okay, so let's use Java as an example. Okay, let's use Java as an example. So I will bring up my BlueJ. Okay, I'll bring up my BlueJ. Okay, BlueJ is a Java editor for high school students. And I kind of enjoy using it because it's very simple. Okay, so let me new a project. So I'm going to put into the same directory as my Python development. Okay, because my course is always using Python development. So I'm going to put it into my demo code over here. Okay, so put it to demo 4 here. Okay, so I'm going to use the demo 4 as my directory. So here I'm going to talk about do while loop. Okay, so do while loop, you create a do while loop. Okay, here I have do while loop. Okay, so do while loop. So do while loop, actually you will go into the do while loop at least once. Okay, at least once. So basically, usually, let's try this one. Okay, let's try this one. Let's try, I have a string. A equals, okay, A, B, C, D, G, A, B, A, whatever. Okay. So now this one must be static. Okay, we would like to put it into the main function. So public, okay, static, okay, void main. That is my Java program. Okay. So I'm going to put my ARGS over here. Okay. System that out the print line. Okay, print here. I use a backslash f. This one just to print page. Okay, nothing important. Okay. Okay, after that, I'm going to find out all the location for AB, okay, and put it into a array list. So I'm going to import, okay, Java the UTIL that array list, okay, create an array list. So this array list is an array list of integer, and we have the AB location. New array list. This will contain the AB's, all of the AB's location. So here, instead of using while loop, I use a do while loop. Okay, I'm going to use a do while loop. Okay, so you use a do while loop and you say the integer, okay, POS, okay, will be equals, okay. Let me see. You may want to use input POS equals 0 over here. Okay. And then you update it with what? With the string A that, okay, index, okay. And here you should have, okay, here you should have your pattern that you want to find AB, okay. So here, let's do this one. Here, let's do this one, make it -1. So the first time I come in, my POS is -1. So here I use the index of using position +1, okay? So this one is, you have this AB, 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 okay? So I search starting from 0 to search for AB pattern, okay? So I may have AB, AB something, okay? So I search for the AB pattern. So the first one, the position I start to search for is POS, that's -1 + 1, that's 0. So I start to search from here. And I should get the first position, okay? And I should get the first position. And I will get the first position. So if POS, okay, is actually greater than equals to 0, okay, then my AB locations will be adding this POS into there, okay. While POS, okay, greater equal to 0. Okay, so if your POS, so this one is also your continue condition. Okay, your continue condition is POS greater equal 0. Okay, so your exit condition will be not POS greater equal 0. It should be POS less than 0. So no file. No file to get out. No file you get out. That's it. And then at the end, we do system.out.print line, print out your AB locations. Okay, so that's the do while loop example. That is the do while loop example, and that's wrong. Okay, it gives you all the location of the AB that we have. Okay. Okay, so that's the do while loop. Okay, and do while loop in Python we don't have it, so I use Java language to show it. Okay, next one is for loop. Same thing, for loop. We don't have for loop in Python. So same thing here. I'm going to show you in Java. Okay. So this one is regular for loop. Okay, regular for loop. Regular for loop, you have 3 conditions. Okay, you have 3 conditions. You have 3 conditions. So public, okay, public, static, okay, void, okay. It's right here in case that you just do for nothing. Okay, this for loop. Okay, and here I say integer I equals 0. Okay, and then I increase, okay, I increase. And right here in the middle, I say system.out.print line and print line of, okay, print line of, let me do print line of I. So you keep printing the I, but this loop, let's see what happened, okay. This one is too long. So what you will see is it keep counting, never end. So it's infinite loop, okay, infinite loop. So here I terminated the execution. So infinite loop. So this one is the same as you put a true over here. So for loop, you have initial condition, continue condition, and the update condition. Okay. So here we don't have initial condition, we don't have update condition. Okay, we don't have update condition. And this scene is equivalent to while true, exactly the same as this. Okay, so that loop and this loop, these two loops are actually exactly the same. Okay, this for loop and this loop is actually exactly the same. So let me take this one out. Okay, two are exactly the same. So we must have some condition to terminate it. So we say I less than 10. Okay, I less than 10. So I equals 0 and I, so this one actually is the same as while, okay, I less than 10. Okay, do this. Okay, and you have the I over here, I increase over here. Okay, so this is similar to a while loop. So compile. Okay, compile, and that's wrong. Okay. So basically, for loop and while loop is the same thing. Okay, it's the same thing. And here we can actually take this one. Okay, the value, initial value, we put into here. This is the initial condition. Okay, this is initial condition. Okay, and this one we can call it, that's the update condition. So we put it over here. Okay, so that this one give you the for loop. Okay, so a for loop has three conditions: initial condition, continue condition, and update statement. Okay, and these are continue conditions. Same thing. When you get out, it will be the inverse. There is not negation of it. Okay, you will get out of the loop. So this one is your for loop. Okay, and for loop in Python we do not have for loop. Okay, in Python we do not have for loop. So how can we actually work out the for loop in Python? Okay, how can we get out the for loop in the Python? So basically, you need to generate your iterator to follow your patterns. Okay, to follow your patterns. So here, let's do for loop. Okay, for loop. So for loop, you do not have for loop. You only have for each loop for each index in range of the array A. Okay. And we have array A equals, that actually it's a list, okay, 2, 4, 6, 8, 10, okay. And then we do this to print out your I, okay. So I is an index in this case, okay. And this range function generated a range object of 0, 1, 2, 3, 4, okay, 5. Length is 5, and it starts from 0 to 4. Okay, so that's the range function we have. So that's print it. Okay, I'm sorry. The previous one not actually done yet. So let me quit it. Okay, I made a mistake. So let me quit it. I don't want to keep there. I don't want to stay there. Okay, let me try a different one. Okay. Try to keep start my Visual Studio Code. Again, I try not to do this using this long code. Okay. Okay, let me try to get my Dewey's University here. Okay, so that is my demo for chapter 4, and I do Windows R, bring the command line, And then I change my directory to this directory here. Okay, pass here. And I do code that I start my Visual Studio Code in this way. Okay. Okay, good job. Okay, so this one we are done. So let's actually do this one no input, so it's okay. Let me actually run it. Okay, so run code. Okay, so it's 1, 2, 3, 4. Okay, so that actually you pick every element from here. So it is, you can also do for, okay, each x in A. Okay, this one is for each loop. Okay, this one is for each loop. So it will be for each element x in A. Okay, you do print the x. Okay. So this one is I, okay, this one is I, is an index. So when we print out the index, it is 1, 2, 3, 4. Okay, it's not the data we want to have. While the other one, we have the element we want to have. Okay, so here, let me put a print. Okay, so this one, it print out index, it doesn't print out the elements. If you want the in the element, you need to use A is I. Okay, and so here I is an index. This one I is, this one X is an element. Okay, so usually for each loop, I use this way to mimic the for loop, and this one is my for each loop. Okay, okay, like that. Okay, the two data are the same. And what can be put over here? You must put something that's iterable. Okay, you must put something that's iterable. Okay, in Java there are also something like this. Okay, there are also something like this. There are also some iterable variable that you can put over there. So these are the for each loop. Okay, so we have the for loop for each loop. So for loop, you put the initial condition, continuing condition, and then you update statement. Okay, this one is for C language. And for each loop, you every time pick an element from a list. Okay, from the list. Okay, so here this it can be a list, it can be anything that's iterable. Okay, so this range 10, you generate 0 to 9. Okay, and here you have the I, and range function is number is similar to the slicing. So 10 means 0 to 10. Okay, and 9 including 10. Okay, so that's actually the follow. So this is different middle break loop. I don't cover it. Okay, so next one is iterable. Okay, iterable and the iterator. What are they? Okay, what are they? So iterable is the a feature of a container. So your list is a container, is iterable. Okay, and iterator is a pointer. So conceptually, you must remember that this one is a container. Okay, so container has a feature of iterable. So container is iterable. A container may create an iterator. An iterator is a pointer. Okay, let's try this one. Okay, instead of using Python, let me use the C++ language first. Okay, so here let's create this one for iterator. One, the C language. Okay, that's C++ language. Okay, so iterator one, the C++ language. Okay, go highlight and install the station or whatever I am fine with it. Okay. Let me go back. Okay, I actually will allow it to install. So let me go back to iterator. Okay, so it may keep going. Okay, it may keep going. It's still installing, but it's okay. I'm going back to my C++ here. Okay, so let me do improve. Okay, here IO string and improve. Okay, vector. So here let's using namespace. And I create a vector of integer. Okay, here let's call data equals create this one. Let's do 2, 4, 6, 8. Okay, so I got this one, and I have integer name. Okay, here I would put nothing. Okay, and here I'm going to return 0 if no error happened. Okay, so now I have the data. I'm going to iterate through this one. Okay, so instead of using the regular for loop, like using the integer, okay, I can write this one. I can write for, okay, integer I equals 0. Okay, I less than data size. Okay, I increase. Okay, and we can actually print now. We'll print now C out, and then data's i's location. Okay, data's i's location. This data is ambiguous. Okay. Okay, here let's don't use equal. Okay, don't use this. Okay, it's initial condition. Let me see. It's actually std. Okay, we use the namespace already. Let me see. Data the size. Okay, let's choose a different name. Okay, let's just choose A. Okay, I think data may because that the std may already use the word data. Okay, so let's change to A to avoid the conflict. Okay, so right here, let me look at the extension. Okay, the extension is done. So let me do run poll. Okay, so run poll. Wait. We do CL. Okay, we do CL here. We should have the endo. Okay, sorry, I should put the endo to change for a new line. So save all. Let's run it again. Okay, so this one is the data. So this one is a regular loop. Okay, so let's do CL. Okay, endo. Okay, so now I want to use iterator. Okay, I want to use iterator. So here I do for, okay, I would have the iterator. So here I would say the vector, okay, int, okay, and then this one I can have iterator. Okay, iterator. So this one create a vector int's iterator itr, okay, would be equals a.begin. So a.begin will return a pointer, and itr would be the pointer pointing to a.begin. So what happened is your A has a data of 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. So this itr is a pointer pointing to the begin portion here. Okay. And then, okay, and then while this itr not equals the a.n, and then your it increase. Okay. So every time you advance your itr, and then while it's not equals the end is the pointer over here. The itr will stop over here. Okay, it actually it keep increasing, and itr by itself is a pointer. It is the iterator type. Okay, so basically right here, what I want to say is your vector of integer is a iterable data type. Okay, and this itr is an iterator. Okay, so iterable data type is a container. Okay, iterator is a pointer. Okay, so because iterator is the pointer, so we can do cl what? Cl itr's the reference is body, is object. We print out the object, and then we print out endo. Okay, so this one will be the object that IT are pointing to, that would be 2, 4, 6, 8, 10. Okay, so that's the way we use that. Okay, so you should get the same result. So these four loops are equivalent. Okay, this for loop and this for loop are equivalent. This one you use the index state variable. This one you use an iterator. An iterator is a pointer. So we start with the A that begin pointer and ending at the end pointer, and I increase. Okay, so that actually is the so-called using iterator. Let's try a third loop. So for each integer x, okay, for each integer x, and that's in my A, okay, and I'm going to do CL. Okay, CL what? CL my x. Okay, so here let me do CL. Okay, and then endo. Okay. So this is another one. Okay, this is another for each loop. Okay, so this for each loop, or for each integer element in the vector. This one is iterable, it's a container, but every time we get an element from it. So this three loop actually effectively would deliver the same result. Okay, this three loop deliver the same result, but different way. Okay, number one is regular for loop. Number two is a regular for loop with iterator. Number three is for each loop. Okay, but they do deliver the same result. Okay, they do deliver the same result. So that's what we call about the iteration over here. Okay, that's the iteration we talk about here. So container, the container list set dictionary, they are iterable. They are iterable, so they can be pointed to by some pointer. So iterator is a pointer. Iterable is a container that you can using pointer to point to. And the next is to find the next pointer. Okay, next is to find the next pointer. And okay, next is you can find the next pointer. So iterator would generate a iterator. Okay, ITER would generate a iterator. Okay, and generator is a special kind of iterator. It always is. Okay, so these are the relationship between iterable, iterator, and generator. Okay, so let's look at it. Okay, let's look at it. This iterable session, let's look at it. Okay, I'm trying to just focus on something that your regular Python course that are over. Okay, that's the purpose of us to study the programming language. Okay, so container is something that you have a data collections. So list, set, dictionary, tuple, and string. These we covered it in chapter 2 already. Okay, so we don't waste our time to do it. Iterable containers are sometimes iterable, sometimes not iterable. We would say most of the containers are iterable. So iterable is some container that you can use pointer to point into, that we call it iterable. Okay, and sometimes iterable also means that the data can be serialized. You can be counted one by one by one by one. Okay, that's called iterable. So here we do have a list 1, 2, 3. We create an iterator, that's Y. We create another iterator that's called G, and Y and G are 2 pointers, and these 2 pointers we do next. We continue to do next. Okay, let's try this one. We don't run the same program. You can look at the sample code in container 4. Okay, so this one, let's try to use iterator. Okay, so this one is iterator. This one I call it number 2 because I already have a C double aspiration. Okay, so I'm going to do it this way. And I have the x that equals, I'm sorry, let me call it A, okay, still a container. So let me use A. 2, 4, 6, 6, A, 10, okay. So we have that. So we have the iterator. Let's call it ITR, okay. So ITR would be the iterator of A, okay. So this is the way that you actually create a pointer. Now, so now we do print, okay. Print your ITR, okay. And then we do next, there's the pointer, okay. And then we do print, okay, ITR. So let's continue this, okay. So we print it and then we next, okay. So let's do this one. Next. Continue a few, okay. So then we actually save this one, okay. We don't have input, so use a wrong code, okay. So that's wrong. Okay, it give you the list object, okay. It give you the list object, okay. So what? So right here, after here, you have the object. ITR by itself it actually is a pointer. So you cannot do that. So let's do this one. We do have this ITR. So let's don't print it. Okay. So let's do next. So this one, let's do A1, A0. Okay. A0 equals this next. Okay. And let's print A0. Okay. So then you have A1. Okay. A1 equals this next. And then we point it to A2. A2. Okay, so something like that. Okay, we are going to repeat. Okay, we are going to repeat. So next. Let me delete this one. Okay, let me copy the whole set here. Okay, put it over here. We would have A3. Okay, and A3. And we have A4. Okay, we have A4. We have A4. Okay. Then we have A5, okay, but we do not have the A5. Okay, we only have 5 elements, so A0 to A4, but A5 we don't have. So let's see who is the A5. So A5 you will have trouble. Okay, so what can we do with this one? It will create. You will create a stop. Okay, A5. You will cause exception, right? A5 you will cause exception. So basically, iterator, sorry. So how can we write a for loop for in this case? Okay, how can we write a for loop in this case? This one, when we stop, it will have an exception. So let's think about it. How can we actually prevent the exception? Okay, so right here, let's do this one. Okay, we would like to use for loop. Okay, so for loop. Okay, so let's actually do get a data. So let's call D. Okay, D will be equals next of this one. That's actually next of the iterator. Okay, so this one it may cause exception, so it will call exception. So let's do this down equals false. Down equals false. So while not done, we will do the repetition. Okay, and we do try. Okay, we do try. We try to get a data, right? So we get a data. So we get a data and we may print it. So we print a D. Okay. But in case that it actually do have the error, so we do exception. Okay. And exception we will do down equal true. And we will get out of the well, okay. So by this way, let's look at it one more time, okay? Initially, not done, we will go into the loop, okay? So we'll get a data using the next function, we get a data, so 2 will be printed. Okay, 2 will be printed. And then continue until you do have a exception, then your down is true, you get out, okay? So here let's do program printing, okay? Okay, so let's try this loop. So this is a combination of while loop and also iteration, and show you how to do handling using the iterator to do programming, to iterate through some data. So right here, if I don't use this one, let me use a G that actually is an empty list. Okay, so ITR2 equals iterator of G. Okay, and here I do iterate through my iterator 2, and it is empty. There's no data. Okay, there's no data. So what we will see is it directly will get nothing, and you only see down. Okay, so this loop is pretty safe. Okay, it's pretty safe. Okay, it is pretty safe. So right here, let me comment this 2 out. Okay, for your own reference. Okay, you can try it later. Okay, let me comment them out. So this one is the idea of using the iterator over the container. What's good about this one is the iterator will go through your data structure, okay? The iterator will go through your data structure, and you can define your iterator, okay? You can define your iterator. So your iterator function in Python is a magic function called iterator function, okay? You can really create something that's actually using next function and the iterator function, okay? In iterator function, that's called iterator. And you can custom design it to define your own ITER function and next function, okay? And that's something you can do. So at this moment, I don't spend the time to do it, but it's okay. You create a class with the next function and iterator function. Okay, so for each loop, you have the iterator, you have some data that's iterable, and you have iterator, okay, and you have the next function to get the data. And the last one, when you miss it, you will create exception, okay, you create exception. That's the so-called for each loop and iterator. So let me try to do this. Okay, let me try to do this. Let me still try to create a iterator example number 3. Okay. Since we want to explain it well, so let's try this. So let's have a class. Okay, let's call it V, okay, vector. So this V vector class will have what? You will have defined the init function, okay, init function, cell, okay, and then here would have a that you can put the data in, okay, so your cell that data, okay, would be equals your a, okay, so that's your a, and a, let's assume that a is a list, okay. So let's see this one. Okay, so let's do this one. So let's do define. Okay, underline str. Okay, so, okay. S equals str cell data. Okay, and then we return s. Okay, so let's try this one. Okay, so we do have a v equals vector. 2, 3. Okay, let's do this one. And that's print v. Okay, so that is a class. We call it vector. Okay, my personal vector. So let's run it. We do see the data 1, 2, 3. Okay, that's good. So now let's define something called iterator. Okay. Okay, iterator is a pointer. It should be a pointer, okay? And you also need to have define, okay, define, okay, next function, okay, so, okay. So next function is to find your next one. So here you should have a your current index, okay? So self index, okay, would be equals 0, okay? So this one you have a iterator, okay? It will return a pointer, okay? It will return a pointer. And this pointer, so you should return what? You should return certain pointer, okay? And iterator will be something you will point into your data, okay? So when you do next, you will find your current index. So you are going to return, okay, and return yourself, okay. Actually, you would return yourself that actually data's self that index, okay. So right here, we should actually pick up your actually return value equals self.data, okay, of the self.index, okay, that you pick up the data, okay. You pick up the data and you will do this, okay. You will do this, you pick up this data and you will self.index, okay, will actually increase, okay, increase, and then you return R. But if you have index out of bound, you would create exception, okay, you create exception. So that's my next function, okay. This ITR would be a iterator, okay, it would be a iterator. So it would be a iterator, and then it may have the next function, okay, it may call this next function. So this one will return, okay, cell, okay, we'll return cell. So return cell, it will go to there. So let's try this one, okay. So try this one. So let's try actually ITR equals iterator of my V, okay. And then I do n equals next of my ITR, and then we print out my n, okay. So let's see whether this one work or not. Okay, so let's try this one. Okay. Vector is not iterable. Okay. Vector is not iterable. We have iterator. Okay. I'm sorry. Here it should be ITER. Okay. ITER, it would be iterable. Okay. One more time. Okay. Okay. So it actually print out 1. Okay. So let's try this one a few more times. So copy. Okay. 2 times, 3 times, 4 times. Okay. Okay, 1, 2, 3, print now, and you got the exception. Got the exception, it actually is fine. Okay, it actually is fine. So the last one, so let's actually try this one. This portion, let's do this. Okay, let's actually delete the last one. Okay, actually, let's actually keep this 3. Okay, keep this 3, and let's do this. Okay, let's do iterator. Okay, equals iterator. Okay, of the B. Okay. So when we create iterator, okay, so when we create iterator, let's do self.index equals 0. Okay, when we create that, let's actually reset it. Okay, let's reset it. So when we create iterator, it will reset the value. Okay, so let's go back to my iterator 2. Okay, so right here, I should be able to copy this whole thing over to my iterator 3. Okay. So basically, it create an iterator down equal first. We do this, we iterate through it. Okay, so here let's do put to separate that. Okay, the cell all. Okay, and then let's do this one. Okay, it's done. Okay, so we can go through the iterator. So one more time, let's do this one. Let's do for each x in my container, that's actually v. Okay, my container that's v, and then pull my x. Okay. Okay, you will create this index out of range problem. Okay, index out of range problem. So here, that's actually, let's try this. Okay, try this. So in the next function, it will create trouble. Okay, it will create trouble. Okay, if you do this for each loop. So we may need to have spatial handling to prevent that to happening. Okay, so we can do that, and that actually is detailed design for each loop data structure. Okay, and that you back it up and you will create an exception. Okay. Okay, here, because we want to try out this for each loop. So right here, let's try another way to handle it. Okay. So if the self the index is greater equals the length of the self the data. Okay. In this case, okay, that's actually because we want to stop the iteration. So that's actually two ways. Okay. Ways what? Ways stop iteration exception. Okay, let's actually raise this one. Okay, instead of general iteration exception, let's raise this one. Raise this one is still be an exception for this, so it's okay. And this one can also handle it. Okay, so let's try this one. Okay, so this one show you like it will be okay. So to make a class or container to be iterable, first you need to design your iterator function. Okay, that you create an iterator function, you reset the counter. Okay, and you return self. Okay, self is that you have an iterator later when you call the next function, it should be calling this next function of the vector. Okay, so it's okay. That is a okay way to write it. And the exception do not show the basic exception, show the stop iteration. Then this one should be fine. Okay. Anyway, that's actually is the idea of the iterator and iterable and the container. Okay. So this portion that's actually work out to here. Okay. So let's continue. Let's continue. Okay, so we had the iterator. Okay, let's move up a little bit. Okay, so here we have a iterator. So basically, you can have a count function from iterable 2. Okay, and your count star equals 3. So count by itself is a counter. Okay, and you will do counting. Okay, so counter, you every time evaluate it, you advance value. This is another idea of iterators. Okay, you can use the iterator tool to do cycle. Okay, cycles through different color, and cycle by itself is a iterable. So you can use the next function to get it. Okay, cycle by itself is iterable. Count is also iterable. Okay. So something like that. And you can do slicing on iterator. Okay. Okay, and you can do islice. So this portion beyond is more advanced. Okay. So know that in each class you have its iterator. Iterator usually you return cell, okay? And it is also a next function, okay? So next function, we produce a result of current code, okay? So basically the next function need to do this, okay? Modify is state, so you move on to the next one, okay? You move on to the next one. So that's that, okay? And a generator, finally we'll write an out destination. The generator are my favorite package, okay? A generator is a special kind of iterator, okay? So generator allows you to write iterator like Fibonacci function, and it has the iterator and that, okay? So it's a lazy factory, okay? So basically we can do generating function. So we from iSplice, okay? Fibonacci current and this is this, okay? So every time you will yield a current, okay, current value, okay? So you start to have this, and every day you update the tuple of the previous and current, okay, previous, but you will yield only one value. So while you are yielding, you will allow it to generate the data. So this one is like you are using it for generation of the data, okay, something like that, okay, something like that. So we do iSlice. iSlice is to getting the index from 0 to 10, okay, and we make it a list. And F is running it 10 times, and you create a list, and we get such data. That's called generator. So generator using the EO function, okay? That's a certain, this EO function is like, when you have a function at EO, you will, whenever you call it once, you get a value. Call it once, you get a value, okay? That's called a generator, okay? That's called a generator. So let's try this one, okay? This one you file true, okay, file true, you get this one. So let's actually go back to use this one that's called generator one, okay? So here let's assume that we had a get function, okay, get function, okay? We will get some data, okay? So I equals 0, okay, without, and while true, okay? And then we will do the following, we will yield I, okay, and I will plus equals 1, okay. We will do that, okay, we'll do that, and that will yield 1, okay. So let's do fluid, okay, get fluid, okay, get something like that. Let's copy it for a few times. Okay, 6 times, okay. So now let me save, okay. Instead of using the run code, let me use this one, okay. Let me use the terminal, okay. So here let's do Python, okay. Generator, okay. So you get generator object, okay. You get generator object. So it did not get the value, okay. It did not get the value. So get, it keep yielding, but you don't get the data, okay. So here let's try this one. Let's try the import, okay. Import the iterator tools, okay. Actually, let's try from iterator tools. Import, okay. Import iSlice, okay. Okay, so here we would have a list equals list, okay. And this one would be iSlice, okay, using the get function from 0 to 6, okay, from 0 to 6, and that's actually finished that and calling my a list, okay. So that is using the get function for 6 times, and then we make it the result to be a list. Function is not iterable. Okay, let me see. Function is not iterable. Type error, function is not iterable. So let me check my code here. Okay, so it's actually rules where true yield current. Okay, current is a value. So where true we yield current, and then okay. So let's see. We do need to have a g function equals get. Okay, g function equals get. Okay, so here let's do g function. Okay. So you make a call, and you start to run, but you have to use a call. Okay, that would be an iterator. So this one, get by itself is not iterator. It's not iterable. It's not generative function. Okay, you need to be the result of this function call. That is a generator. Okay, that is a generator. Sorry for that. Okay. Okay, so that's the idea of generator. Okay, so generator is a special kind of iterable. Okay, the basic idea is that you create a function. Okay, the function is generating function, but you keep it running. So it's just like a factory. Okay, it keep running. Whenever you request data, you advance. Request data, you advance. By yourself, you keep running. So this one is a Fibonacci function, but you do need to use that. This one is the iterator. Okay, this one is iterator. This Fibonacci function is generating function, is not iterator. Okay, so that's the idea of generating function and iterable. Okay, iterator. I'm sorry, iterator. So let's actually try another one. Okay, try another one. So here is something like this. Okay, let me comment it down. Okay, let me comment it out. Comment this one out. Okay, so let's cut this one and put it over here. Okay. So here, because G is a iterable, so let's do list of G. Okay, so let's just do list of G. And G actually is, okay. So G in this way, G you call a generating function, and G will be a generator. Okay. 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 Okay, so that's how generator being used. So generator is a special kind of generator is a special kind of generator is a special kind of iterator. Okay, and generator have all the feature that your iterable has, iterator has. Okay. Is actually, but generator will need to have a generator function. Okay, you need to have a generator function. Okay, you need to have a generator expression and the generator function to make it work. So get function is a generating function. Okay, and then G is a generator. Okay, G is a generator. Okay, and then we create Fibonacci functions. Okay. So let's see, that's actually the yield function, okay? So the yield function actually will hold back the data, and then when you do it, it will actually produce the data later, okay? Okay, this is the so-called generator. Okay, so generator is a special kind of iterator, and iterator is a pointer to iterables, okay? Okay, these are the key idea, okay? So we finished that. Okay, we finished that. Then function. Okay, function call. A function performs specific task. Given state, condition, and the post condition. It has a name, parameter, and return value. Okay, I think everybody knows what function is. So right here, let's go through the slides. Function is helping the modularization, code reusable, packaging, teamwork, abstraction, and readability, okay? And you have code section, subroutine, procedure, operation, function, method, lambda expression. These are of similar meaning, okay? So we go to some subroutine and then return. So when you call a function, the calling process, we call it, we actually go to the subroutine and then we return to here, okay? So when we go to the subroutine, this period, we call it prologue. When we return, we call it epilogue, okay? When we return, we call it epilogue. Okay, so procedural abstraction, recursion, non-concurrent, concurrent and non-determinate. This different topic, okay, recurrence, we will talk about in functional programming portions, and concurrence, it is an important topic, but for this course, we are not going to touch it, okay? And if you are interested for the concurrency, you can look at the previous year's video, okay? Previous year's video. Okay, so function get input and provide output, okay? It's basically abstraction, reusable, and library, okay? So function has a function signature, like including the function name and parameter list, okay? And parameter list can have default value, can have a grouping effect, okay? Can have grouping effect. So once you do grouping effect, you will create a list for you, okay? You create an iterable data structure for you, okay? And there's a hint. The hint is the return data type, okay? Hint is return data type, okay? And Y is a local variable. Y is a local variable, and you can also do return statement. So a function including the function signature, function name, parameter list, return type, and local variable and return statement. Okay, these are the basic functions statement. And your function can call, and the function can call another one. Okay, so you will have call stack. Okay, so call stack including the return address, okay, return address, including the local variable and also including the parameters, okay. Exception, we explained it already, okay. Recursion, a function calling itself is called recursion, okay. And for recursive programming, we'll touch it in chapter 7, 8, 9, the functional programming, okay. So it's a very useful rule, okay, for recursion. So recursion is a routine that call themselves, okay, call themselves. And iteration and the recursion are equally powerful, okay, and they can convert to each other, okay. So here we have a function calculating the GCD, okay. So if m equals n, we return one of them, okay. It's actually already the GCD, okay, greatest common denominator, okay. And if m greater than n, so then m is bigger, so we try to minus it, and then we return GCD of it 2. So we basically, every time we minus the bigger number minus the smaller number, okay. What this one really means is that if we have an n that equals a times f, and f is your GCF, what is common factor or GCD, okay? Sometimes these two terms are mixed. So m equals v times f. So if you actually have found the f that is your GCF, okay, then your a and b should be prime to each other. So this one prime to each other. So if we have m minus n, that would be a minus b times f. So this one, m minus n, is also a multiple of the f. So by the theory, this f still be a GCF for n and m not minus n. Okay, f is also a common factor for it. Okay, so this is the background knowledge. But tail recursion means that after the computation, there's no more operation. So you do recursive code, there's no more plus, minus, or times to calculate the result. Okay, that's called tail recursion. And tail recursion is a good feature for code optimization. Okay, the compiler can optimize on tail recursion. Okay, so this one is okay. That's a tail recursive function. So if you have a function that continue to do some operation after you return some value from smaller case, then it's not tail recursion. Okay. So tail recursive code can reuse the subroutines code frame. Okay, and that would be easier. So we actually can do optimization for compiler. Okay. Okay, so that's that. And this one is another version. Okay, another version. We do provide different GCD version. You can study it. Okay. Different way to calculate it. Okay. That's the GCD 3 and 4 actually are using while loop. Okay. They are not recursive, so they are iterative methods. And recursion is inefficient. Okay, so this one is inefficient because this one would be exploding in exponential time. So usually you use a iterative function may be faster than if you do not write the recursion correctly. Okay. So this one we do use the while loop to implement it. Okay. It will be faster than recursion. Stack layout. Okay. So when you call a function, you will get a call frame, and call frame exists in your call stack. Okay, so you store your parameter, return address, and local variables. Okay, that's called your call stack. Okay, and call stack you will have static linking or dynamic linking across the stack call frame. Okay, and this depends on different language. That's we call it deep binding or zero binding. Okay, deep binding or zero binding. And Python is using deep binding. Okay, so a stack may have parameter, local variable, temporary, and some bookkeeping information. Okay, heap is used to store object. Okay, and bookkeeping including the return program counter. Okay, program counter, save register, line numbers, and display entry and static. Okay, so these are something stored in the code stack. Calling sequence, okay? So your stack need to be maintained by the calling sequence. So to enter into the sub-function, we call it prologue, okay? Get out, we call it epilogue, okay? And here prologue, you do prologue with UE, that is the same word, okay? It's the same word. Okay, epilogue, you say. You write epilogue. These are two same. These two are same word. Okay, these two are same word. So prologue need to do these. Okay, passing parameters, saving the return address, changing the program counter, then save the register. Okay, and then changing the frame pointer to refer to the new frame, execute the initial code for the new object. Okay. Epilogue is when you return. Okay, you need to pass in the return parameter or function value, execute the finalization code for the local object, allocate the state frame. Okay, restore the store register, restore the program counter. So epilogue is to go back to the main function. So because of this, each functional code may have what overhead. Okay, might have overhead. So in compiler, we do want to optimize it. Okay. So this one is the detailed picture of the calling sequence. Okay. Here, remember, it is not call stack. It is the execution time. Okay, this is execution time. This is not call stack's content. Okay, this is execution time. So calling your procedure would have these different things to do one by one until you finish your program and come back. Okay, this is not called a state diagram. This one is the calling sequence example. Okay, so that's calling sequence. So calling sequence come out divided into caller save and callee save. Okay, caller is the mother function, callee is the child function. Okay. So here your register file has different responsibility for caller save and callee save. Okay. And sometimes the RISC machine like to use a register window, so they can share some register between the caller and callee. Okay, and this is sharing of the registers. And here we list down the typical calling sequence. Okay, you can study it's quite long, so we don't go into the details. Okay, and the low-level virtual machine like ARM, you can low-level virtual machine is a layer of virtual machine, such as a executable code. So you can compile your program to a bytecode for this low-level virtual machine. So low-level machine become popular because you can make it really at a very low level, but machine platform independent. Okay, so nowadays many C or C++ like to compile to low-level virtual machine as well. But low-level virtual machine will need to handle this kind of the prologue and epilogue, okay, because it is dealing with the machine, okay, dealing with the machine. Okay, so here list down the prologue and epilogue for the low-level virtual machine. Okay. And because this machine level thing is not our main focus, so I don't spend too much time to go into these different details. Okay, so this is the end of chapter 4. Okay, because we have limited time, so some topic we don't have time to go over it in too much detail. Okay, because I need to limit my total lecture time for each chapter. Okay, thank you. Bye bye.